Okay, this next question is swinging balls. So for this, basically someone's swinging a ball vertically, and we have to do some calculations. And the first one is calculate the size of the centripetal force acting on the ball at the instant shown in the diagram. So that's when it's in this position here, travelling at 4 meters per second. For that, we just use this equation here, this centripetal force equation, and we just substitute in the values. So we've got the mass of the ball, which is 0.250 kgs, multiply it by the velocity of the ball squared, and then divide that by the radius. And we come out with a force of 3.33 newtons to 3 significant figures. And then on to the next question, explain why the ball moves fastest at the bottom of the circle. So why is the ball moving the fastest down here? They're not very clear about this in the question, but the ball's moving faster because the gravitational potential energy that the ball has at the top has been converted into kinetic energy at the bottom. So that means that the ball must be going faster because the mass of the ball hasn't changed, the kinetic energy must have changed. So you could write that something like this. EGP has turned into kinetic energy. Therefore, the velocity must have gone up. So if you think about this, EK equals half mv squared. If that's gone up, this remains constant, so this must go up in response. Okay, then onto C. We've got these two diagrams here. So this is part I over here, and I possibly haven't given myself enough space. So on here, I need to, this shows the weight forces acting on the mass, and they are the same regardless of where the mass is, or this in the swing. And then I have to assume that the tension force is non-zero at all points, which means there must be some tension force acting towards the centre of the circle here at the top. It's not going at the lowest possible velocity, where the only force acting at the top is the weight force. Draw vectors to show the relative sizes of the tension forces at the top and bottom. Okay, so it's going to be going slower at the top, and thinking about this equation here, if it's going slower at the top, that means there's less centripetal force required. So I'm going to draw my tension force here at the top, quite small. Okay, this is the force tension, which means at the top the centripetal force is a sum of these two forces here. So I guess if I did that over the side, you'd have the weight force like so. I'm trying to draw these roughly to scale, as in my diagram over here. The tension force like that, which means the centripetal force is the sum of these two here, F, C. So then, thinking about how to draw the tension force in this one to scale, the centripetal force at the bottom must be greater than at the top. Because the velocity is increased, and we discussed why that was in question B, that means the centripetal force must have increased. So I'm going to draw a little vector diagram over here and then translate the tension force onto this diagram. So I'm going to draw the centripetal force, the total force, first. I'm drawing it bigger than that force here because of the reasoning from question B. So this is the centripetal force, and this is made up of the weight force and the tension force. So I'm going to draw the weight force first, and then I'm going to add to it the tension force. And an interesting thing happens here. The weight force is still acting vertically downwards. I've drawn it a bit big, but you get the idea. It's supposed to be the same size as this one, which means the tension force is going to be from here all the way up to here, Ft. So I need to draw that on my diagram. I told you I didn't give myself enough space. Here is Ft. Okay, so the tension force plus the weight force must add to give the centripetal force. So it's a much bigger tension force here at the bottom than at the top. Okay, moving on to the next part of this question, which is II, part 2. Use the same scale, draw the centripetal force on diagram 2 at these two positions. Okay, so I've already done that, so I can just copy these two centripetal forces from over here and draw them roughly to scale. So this is FC, and here it's this one here. So that's about the diameter of the circle. So that's FC. So often if you get a problem like this, it's a good idea to draw these vector diagrams to show your reasoning. That means if you don't get the scales quite right, you're demonstrating quite a lot of understanding in these two diagrams here. So this applies to the bottom of the system, and this applies to the top of the system. Okay, moving on to the last question, part D. This is a tricky one. Like this is hard, this is also hard. I like this question because it's conceptually quite good. This one is just mathematically difficult. This is going to be a bit easier when we look at simple harmonic motion because you're going to be a bit more familiar with doing this kind of thing. Right, so let's get into it. We're trying to work out this angle in here. So if we know that the speed of the ball at the top is decreasing as the ball comes up, and this is the lowest speed at the top, that speed is 3.43 meters per second, and at some point before that, at a lower height, the speed is 4.00 meters per second. And we need to work out at what angle does this occur. So there's a few steps to working this out. Okay, step one is answering the first part of the question, which is to show that this is the velocity at the top. And the way we do that is by equating these two together. So we get mv squared over r equals the mg. We get out our cancelling pen, get rid of the masses. And then we're going to rearrange this and make v the subject. So I'm going to take r from the bottom on this side and put it on the top over here. And then, because it's a square on this side, I'm going to move that over to the other side and we get a square root. Now I've got all these values, these are all known, so I can substitute those in. 1.20 times 9.81, and I can solve, and I get 3.43 meters per second. So that's the first part of the question, and I know that's right because it's a show part. Okay, then the next thing is to consider, okay, what angle must be in here? And what I'm going to look at, I'm going to consider this in terms of energy. So this ball has lost some energy, some kinetic energy as it goes to this position. It's lost it to gravitational potential energy. So this height in here is of interest to me, because if I know this height and I know this length, I can then work out this length and from that calculate the angle. So what does that mean? Well, it means the change in gravitational potential energy of the bob going from here to here must be equal to the change in kinetic energy. Whoopsie, okay. Because the kinetic energy that is lost has been converted into gravitational potential energy, and that change must be equal. And how do I work out the change in kinetic energy? Well, it's EK final minus EK initial. Now the reason I'm showing all of this working is because of the square in this equation. Makes it a little bit tricky. Okay, so over here I know this is equal to the gravitational potential energy is equal to mg delta h, with delta h is this height here. So I want to work out this little height in here, and I do that by working out the initial kinetic energy, the final kinetic energy, Vf squared minus the initial kinetic energy. Here, again, the masses are going to cancel out. Get rid of those. And then I'm going to substitute in the values that I know. So first I'm going to take out a factor of, take this half. So this is, if I simplify this down, wow, it's really windy today. Vf squared minus Vi squared. I'm going to take this half over to the other side. So I get 2g delta h is equal to, and here I'm going to substitute in my velocity. So the final velocity is the one that I calculated previously. Don't forget to square it, minus the initial velocity, which is this one here. Okay, so now I can solve delta h, which is this height here. And so these come out as negative 4.2351, and that's going to be all divided by 2 times 9.81. And I get a change in height of 0.2159 meters. And that's to 4 significant figures. Okay, so that's this height here. This is 0.2159. So now I need to work out this length here. I'll call it L for length, and it's going to be equal to the radius, which is the total length of the string, minus delta h. Oh yeah, I'll put lots of equal signs in, eh? So the radius there is 1.20, and I'm going to subtract from it this height here, and then from that I'm going to get a length of this side of the triangle of 0.9841 meters. Cool, so now I've got two sides and I need to work out an angle, so it's become a trig problem. To work out this is a cosine problem. So cosine of theta is equal to the this side here, 0.9841, divided by the hypotenuse, which is the radius of our circle, and then I need to solve for the angle. And if I put all this, what am I doing? If I put all this into my calculator, I come out with an angle of 34.9 degrees to 3 significant figures. Alright, and that's that problem done. Pretty challenging. Alright, hope that was helpful.